we only have a few problems left, I think. 4 of them. Few problems left for section 5.3. And each one of these, I will tell you, each one of these is very similar solving-wise. It's just using a different formula, okay? I told you guys yesterday that I would not expect you to memorize those formulas. I will give those to you. But solving each one of these is going to be a very similar format, just using a different formula. So, population growth. They're going to have us use the continuous compounding for population growth. Okay? So now they do not give us the formula. We have to actually plug stuff in. Colton, get your notes up. Great. Pay attention. Okay. The world population. I just did an arrow. Did you write it?
No.
Okay, great. The world population in 1950 was about 2.5 billion people. And has been increasing at approximately 1.85% per year. Write the function that gives the world population in year X, where X equals 0 corresponds to 1950. Okay. So the X equals 0 corresponds to 1950. That just tells us that, like, the start the world population is 2.5. If they don't designate X equals 0 as 1950, we don't know where we're starting from, okay? So they just do that to make it easier on us. So we need stuff to plop into A equals PE to the RT power.
2.5.
Okay, so where does 2.5 go? P, it's like your principal. It's like what you're putting in, right? So 2.5 is your P. E stays E. E is just a number, right? What is E equivalent to? Do you remember? Don't look. 2.718 approximately, something like that, right? 2.7, okay? R, what's the R?
The rate.
R is the rate, which is?
1.0.
Yep, but you need to put it as a decimal, so 0.0185, okay? And then what's T?
Time in years.
Time in years, which is? They call it X. They just said put X in, because all we're doing is writing an equation for this. Yes, it's just saying write the equation for this, right? Okay, so we're not actually solving for anything. We're leaving X as X. We're leaving X as X, okay? So this is all that we need. That's it. That's all that it tells us to do. Okay, that's it. All right, now they're going to introduce us to exponential growth, which is a similar model to what they had before, PA to the X power, okay? Or they will also write it as P times 1 plus R to the X power, whatever. Bacteria growth. This is another one where we are finding the equation, and then now we're actually plugging stuff in for it and solving some things, okay? At the beginning of an experiment, okay, look for those words at the beginning. That means what you're starting with. At the beginning of an experiment, we're starting with 1,000. Where does 1,000 go? That's P. That's my principal. In the beginning, that's your principal. That's what you're starting with, 1,000. 5 hours later, what's 5? I'm just going to list my variables over here. P is 1,000. 5 hours later, what's 5? Time, that's T. There are 7,600. What's 7,600 equivalent to? Yeah, it's like your A or your F of X. They write it as F of X. We wrote it up here as A. That's my, I think of A as being like the after amount, okay? After amount is 7,600. How many bacteria will there be after 24 hours? Okay, so where does the 24 go? It's also time, so what we have to do now first is we have to wait on this part. Until we have established our equation, we've got to wait for the 24 hours, okay? Wait for the 24 hours. Okay, so let's fill in our formula here. I'm gonna move my 1,000 over. Let's use exponential growth. Yep, let's do that. 1 plus R to the 5th power equals 7,600. There we go. Okay. So we have to find R. We don't know at what rate this bacteria or whatever it is growing. That's what we need to find. Then, as soon as we found that, as soon as we found the rate at which it's growing, now we can plug in 24 hours, yeah? Okay? Not really. Not really. The only time we have to use ln is when we're solving for the exponent. The exponent we know. Okay, so let's just unwind this equation and see what we get. Okay, this was kind of weird. What are you gonna do first? What are we solving for, by the way? What variable? R. Here's R. Okay. What are we doing first? Divide by 1,000. Did you do that without a calculator? Maybe. 7.6. Okay. And this is what? No. 1 plus r to the 5th power. Okay, now what do you do? Yeah. Now I need to get rid of the 5th power, so I'm going to take the 5th root. Okay, so you're going to need a calculator for that one. What is the 5th root of 7.6? Because I don't know what times itself 5 times will give me 7.6. What is it? Do you guys know how to do 5th root on your calculator?
Wait, could you do ln?
Math one, go down.
No, I would not, just because when you're solving for ln, you're trying to get rid of stuff and pull the exponent down in front. And that's not really, you might have been able to, but it would be weirder steps than what this is.
1.5.
Yeah. 1.5, exactly?
No, it's not exactly. But
Give me 2 decimals. Give me 2 decimals.
it's 1.5.
1.5 what?
0.
50, okay. Perfect. 1.50, and that's 1 plus r. So what is r?
0.5.
R is 50%. Our growth rate is 50%. That means it's like 150% is my like expansion rate or whatever, you know. It's growing pretty quick. Okay, so now over here I have the formula A equals 1,000. Now I know that 1 plus r is 1.5 to the t power, and this time I want to know after 24 hours. Now I just plug everything in. Now that I know my rate, which was what I was finding before, now I can just plug stuff in. Okay? How many bacteria are we going to end up with?
Hey, can you tell me the last 10 minutes of class are? Hey. I'm too lazy.
Okay. All right, what's the number? Sorry, I'm dying. Ugh. What do you got? 0.2. Bacteria. Oh my gosh. There we go. All right, I think I'm better. The problem is every time I cough, I feel like I'm gonna throw up. Like that's just the way it works.
That's called
No.
what?
0.2 bacteria. So you really don't need the 0.2 on there because you can't have 0.2 of a bacteria.
You
I
can.
guess it's kind of like it's splitting at that
You
point,
can have
right?
a very, very tiny.
Hey, now, here's my question to you. Is it realistic that this would continue on forever and ever and ever? They don't ask this question.
Yes.
Is it realistic that this bacteria would continue to grow forever?
No.
As
No.
long
As long as the food
as its food source continued to,
As long as
like,
they
provide
stay
for
fresh.
it, right? Okay. So
So
there's that.
Those are questions like on the
Alright.
ACT.
Okay.
At least when I
We skipped to that.
What?
We skipped to radioactive decay.
Okay, we'll talk about this one. I'm not going to skip it entirely, but we'll talk about this one, okay? So, number 8. Listen. Number 8 is going to be the same except one thing.
What?
This says, you're not listening.
What?
This says exponential decay. My formula before was 1 plus r to the t power. When you're doing, listen. When you're doing exponential decay, what changes out of my formula? It's going to be a minus what? Minus where? R. It's going to be a minus r. So, for decay, this would be 1 minus r, because 1 plus r is going to end up with a number bigger than 1, right? That's a growth. A number smaller than 1 would need to be 1 minus the interest rate, right? Or the rate of growth. So when you're doing decay, use that formula. I'm not going to go through example 8. Is that okay if we skip?
Yeah.
Sure. Let's go to number 9. This is...
This is Cometry.
Oh, this is also number 8. Number 9. Radioactive decay. Here's your formula for radioactive decay. Okay? They give us some weird variables here, so let's talk about them real quick. P is still your principal. Okay? X. What is X? What is X in here?
Radioactive decay began.
What?
How long it's been decaying for?
So this is the time. X is your time. Now, what is H, or whatever that word? Yeah, H. What is H? H is the half-life of the substance. You guys who take science class, have you guys talked about like carbon-14 dating and stuff? Carbon-14 is 30 years. Okay, so what they do is to figure out like how long dinosaurs have been like dead. Is they will take samples of the fossils of the dinosaurs or whatever, figure out how much carbon-14 is in that, and then they can backtrack and figure out how long the thing has been dead. Because after 30 years, there should be half as much carbon-14 as there was to start with. So that means after like 10,000 or 11,000 years, there should be a quarter of what it was before. There should be an eighth after 3 cycles of that, etc. Right? They figure out how much is broken down. Yes, sir.
For people in chemistry, we do that in second semester.
Yes.
Junior high and high school quiz bowl members that are doing
Quiz bowl members, I'll give you this sheet when you come back.
I don't
Okay. So, radioactive decay. When a living organism.
Wait, what sheet?
So, I'll give you my sheet, so you can copy this down. Okay. If you are quiz bowl, you can go radioactive decay. Let's plop our numbers in and be done. When a living organism dies, its carbon-14 decays exponentially. So it decays, okay? An archaeologist. An archaeologist determines that a skeleton of a mastodon. I had to look this up last year. Do you know what a mastodon is?
Dinosaur.
It's like a big, it looks like a big rhino, kind of.
Yeah,
Yeah.
but it doesn't have horns.
But it doesn't have horns? Okay. Has lost 64% of its carbon. You're not listening. I'll just make this take longer. 64% of its carbon. Okay, there is a trick to this problem. It's not just straightforward like you think it is. Okay, the half-life of carbon-14 is 30 years. Estimate how long ago the mastodon died. Okay, here's the tricky part. Here's the tricky part. So in my formula, I'm just going to write this out. A equals P 0.5 to the X over H, okay? X is how long. Estimate how long. This is what we don't know. It's the formula. It's formula. Okay, I'm just rewriting the formula. X is what we don't know. That we do know the half-life of carbon-14. We do know that this is 5730. Shh, be quiet. Be quiet. There's no such thing as full life, okay? 5730 is the half-life. Okay, now, here's the question. How big was the mastodon to start with?
Big boy.
We don't know what the principal is. But we do know that 64% of it is remaining after that many years, right? Or however many years. Well, then listen. Just be quiet.
But you said there's no full life. Well, then how can you have full life?
I'll come back there and explain it to you. Okay, so I don't know how big the mastodon or how much carbon-14 it had to start with. That's where I'm struggling, okay? So let's make up our own numbers. Let's say that the mastodon had 100 grams of carbon-14, whatever. Let's say our principal was 100. Okay, I'm just plopping these numbers in. Let's pretend for right now that the mastodon had 100 grams of carbon-14. Okay? It said that 64% of it is remaining after X number of years, and X is what we're solving for. So if we're starting with 100, what is my A, my after amount, going to be?
64 grams.
Yeah, what's 64% of 100? 64, right? Okay? So it doesn't matter how big the mastodon was to start with. Maybe he was like 1,200 grams, right? But I chose 100 because 64% of 100 was really nice, right? No matter what this principle is, you're going to first divide that over, and no matter what, you should get 0.64 on this side. Does that make sense? So maybe it was, I don't know, maybe it was 500, okay? But then this would be 64% of that, dividing 500 over, that's going to be 0.64 no matter what. So I got to make up my own numbers just as long as this is a 64% relationship of that.
Maybe
Does
just
that
start
make
with
sense?
0.64.
What?
And then just, like,
If you want to
100.
skip that step, you can start with 0.64. Yes,
And
exactly.
then you
And then there's
multiply
no principal.
why didn't you multiply the 100 by the half? Yeah.
Because you have the exponent that's connected.
Good question.
Yeah, the exponent.
Exponents come before multiplication, right?
And then
So we've got to treat those separately. We've got to divide the 100 over first. Okay, so now we have to use ln in this problem to get the exponent down.
Why can't you multiply? Never mind.
Because he's an exponent, you're not multiplying. Okay? So when I'm solving for an exponent, you have to use ln. So I'm going to ln both
Is
sides.
it 0.5 or 0.05?
It's 0.5. I keep writing the wrong number. 0.5. There we go. 0.5. There we go. It is 0.5. You're right. Okay? Now I natural log both sides. And by doing that, I can bring that front part down in front. ln of 0.64 equals x over 5730 times ln of 0.5.
Oh gosh, dang it.
Okay? All right. Then what can you do?
Divide the
Divide the ln
ln.
of 0.5. Okay? After you do this so many times, it's kind of like second nature. You can kind of figure it out. Okay? So what's ln of 0.64 divided by ln of 0.5?
0.644.
Point what?
644.
644. Okay? Equals x over 5730. Okay, just wait a second. Just wait a second. Before we get the answer, just wait. Has my mastodon split in half yet? No. Right? Because he's 64%. In order for him to split in half, he would have to be 50%. So he has not yet split in half. That means my number of years has to be less than 5730, correct? It's less than 5730.
Junior high and high school FBLA members.
Just wait a second. We're almost done.
Junior high and high school FBLA members.
So multiply by 5730 across how many years has he been dead?
3,689.3 or 0.29.
Years. We'll go 0.3. So he's only been in for about 3,600 years, right? Okay, so think about that if that seems reasonable. He's not yet split in half, so we know he has not yet been dead for 5730 years. Does that make sense?
Yeah.
That's what happens with radioactive decay. There he is.
Wow.
Okay? That was a tricky one because they did not give you principle to start with, so you can kind of make up your own principle, or you can just, like what Liddell said, just set it equal to 0.64 to start with, yeah?
It'll also get a lot harder when you get to smaller percents because that one was super easy.
Right, exactly. There you go.
Like if you have like only 1% of